Okay, in this video we're going to go through the very last case of circles. So the very last circle theorem says that if I was to draw a perpendicular bisector through all of the sides of a triangle, they will intersect at the middle of the triangle. In this case, they will intersect exactly in the center of the circle. So that's a fact that you need to remember, a circle theorem that you need to remember for questions that we're now going to do. So we're going to look at the first example in a moment. So here's an example where the points A, B and C all lie on the circumference of a circle, and we need to show that AB is the diameter of a circle. So that's going to be straightforward. So we're going to work out the gradient of AC and show it's exactly perpendicular to BC. So we're going to work out the gradient of AC, standard formula y2 minus y1 over x2 minus x1. So we're now going to get, if I'm trying to find the gradient of AC, so it's 9 minus 1 over minus 4 minus minus 8, which gives me 8 over 4. And I get 2. So the gradient of AC is simply 2. So now I want the gradient of BC. Same formula, y2 minus y1 over x2 minus x1. So now we're going to work out the gradient of BC. So it's going to be 5 minus 9 over 4 minus minus 4. Minus 4 over 8, in other words, minus a half. So if we were to multiply those gradients together, we should get minus 1 if they're perpendicular. So MAC times MBC, we get exactly that. 2 times minus a half is exactly minus 1. So we can say that AC is perpendicular to BC. Therefore, triangle ABC is a right angle. It is a right angled triangle. Where angle ACB is 90. Therefore, AB is the diameter of a circle. So that's part A. Now, for part B, we're assuming that we know that, even though we've shown that AB is the diameter of a circle, I'm going to pretend that we don't know that. And what we're going to do a perpendicular bisector through the point AC, like so. Just do that in one colour. Has to go through the midpoints. So bear in mind this is a sketch, just for your understanding. It's not drawn to scale. And we're going to do the same thing through BC. So I'm going to draw a perpendicular bisector through AC, and what's going to happen is it's going to go through the center of the circle. These perpendicular bisectors, like so. Let's see if I can control a little bit. So it's going to hit there. Okay, so I'm going to do this one in, say, pink. So, as a rough sketch, so what we're going to show is these two perpendicular bisectors, one in pink, one in green, are now going to intersect exactly in the center of the circle, okay, which hits, in our case, the diameter. Okay, and we're going to then work out the equation of the circle. Okay, please bear in mind that this is not drawn to scale, and it's only a rough sketch for your understanding. So let's work out, we've got the gradient of AC and BC. And what we're going to do, we're going to work out the equations of these lines. Okay. Now, first of all, we need to work out the midpoint of AC and the midpoint of BC. So let's do that first of all. So we're going to say that the midpoint of AC, standard, what we've done before, is -8 plus -4 over 2, and then we're going to do 1 plus 9 over 2, and that's going to give me -6 and 5 respectively for the midpoint of AC. We want to find the midpoint respectively of BC, so that's going to be as follows. We're going to do -4 plus 4 over 2, and we're going to do 9 plus 5 over 2. And there, for the midpoint, we get 0. And 9 plus 5 is going to be 14. 14 over 2 is going to be 7. So now that we get the midpoint of both of those, AC and BC, we can then go ahead and work out the equation of the line. Now, ultimately, you might be thinking, why am I doing this? Well, example 14 in the book essentially gets you to solve a simultaneous equation. So I'm trying to do two things in this question. So it's the same, rather than repeating another example, it's the same, more or less the same procedure. So we're going to work out the gradient of the perpendicular bisector to AC. So let's do that. So the gradient of the perpendicular bisector to AC is -1 over what we found earlier. We found the gradient of AC to be 2, so that's -1/2. So the equation of the line, let's put the equation of the perpendicular bisector. So just writing this down for your understanding and clarity. Equation of the perpendicular bisector to AC. Perpendicular bisector to AC. Well, we've now worked out that the gradient of that line is -1/2, so it's the standard formula y minus y1 is m times x minus x1. In our case, we want the midpoint of AC, so in our case it's y minus 5. Now we said that the gradient of the perpendicular bisector was -1/2 of x minus the x coordinate of the midpoint, which is -6. So we get y minus 5 equals to -1/2 x plus 6. Now times everything by 2. So we get 2y minus 10 is -1 times x plus 6. That's going to give me 2y minus 10 equals -1x minus 6. So bring everything on one side, x plus 2y is equal to 10 minus 6. So our first simultaneous equation is x plus 2y equals to 4, and we're going to label that as our first simultaneous equation. Now we're going to do exactly the same thing for the green line. That's going to be, we need to find the gradient of the perpendicular bisector to BC. So let's do that in the same manner. So it's the gradient of the perpendicular bisector to BC is -1 over what we found earlier. So let's have a look. So we found the gradient of BC to be -1/2. So it's -1 over -1/2, which is +2. And we need the midpoint of BC, which we found to be 0 and 7. So it's y minus y1 is m times x minus x1. So we said it was 0 and 7, so it's y minus 7 equals to 2x minus 0. Y minus 7 is 2x minus 0. So y minus 7 equals 2x. So we could rearrange for that to say 2x minus y equals to -7 as our second simultaneous equation. So writing the first one underneath it, x plus 2y equals 4. I'm going to take all of equation 2 and times it by 2, so we get 4x minus 2y equals to -14. And that's going to be equation number 3. X plus 2y equals 4. That's equation 1. So we're going to add both equations together. So 5x equals to -10. X is -2. Let's do a substitution. -2 plus 2y equals to 4. 2y equals to 6, therefore y must be 3. So we now know that the points of intersection of the pink perpendicular bisector and the green perpendicular bisector is now the center of the circle, which is now at -2 and 3. So we can say the center of the circle is at -2 and 3. So now what we need to do is work out the radius. So we've done this in the previous video where we're going to draw in the radius. So I'm going to go from, now we established the center, so we're going to go from here to the center to the point C and call that R for the radius. So C is -4 and 9. Let's write that in. So C is -4, 9. So what we need is the radius squared. So the radius squared is going to be -2 minus -4 all squared plus 3 minus 9 all squared. The radius squared is going to be 2 squared plus -6 all squared. So r squared is 4 plus 36. So we get r squared to be 40. Now we have the center of the circle, so that therefore the equation of the circle is x plus 2 all squared plus y minus 3 all squared equals to 40. Now here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So they've told us in this question that ED is perpendicular to EF. So the first thing we ought to do is to work out the gradient of DE. Now that's going to be B minus -3 over -10 minus 12, which works out to be b plus 3 over 2. Now we can do the same thing for the gradient of FE, which is b minus 5 all over minus 10 minus 2, which works out to be b plus 5 over minus 12. Now, because they're perpendicular, that means the product must be equal to minus 1. So we can say b plus 3 in brackets, as in all of it in brackets, over 2 times b plus 5 over minus 12 must be equal to minus 1. So we essentially get b plus 3 times b plus 5 all over minus 24. That's equal to minus 1. So we're going to times both sides by minus 24 like so. So essentially they cancel out. So we end up with b plus 3 times b plus 5 equals to 24. So expanding the brackets out, so we get b squared plus 8b plus 15 equals 24. So we get b squared plus 8b plus 15 minus 24 equals to 0. B squared plus 8b minus 9 equals 0. We're going to solve our quadratic equation here. So we get b plus 9, b minus 1 equals 0. So our solutions are b equals to minus 9 or b equals to positive 1. But since b is greater than 0, therefore b is equal to positive 1 as required. Now you want to find the equation for C. So here we don't need to really work out both perpendiculars because we know that the angle in a semicircle is a right angle, hence that's going to be the midpoint, hence the center of the circle. So we're going to find the midpoint of D and F. So let's do that. So that's going to give me the following. So we want to find the midpoint of both of those. So it's going to be minus 12 plus 2 over 2. So midpoint is minus 12 plus 2 over 2. Let's just check. Got that right. And minus 3 minus 5 over 2. Okay. Followed by minus 3 minus 5 over 2. So we get the center of the circle to be minus 6 over 2. Well, sorry, that's going to be minus 10 over 2 is minus 5. And then we're going to get minus 8 over 2 to minus 4. So we get the center to be minus 5 and minus 4. Now what we want to do is work out the radius of the circle. So I'm going to go here to there and say that's r. So we want to find r squared. So f is 2 and minus 5. And we've got the center. So let's write down f. 2 and minus 5. So you want to find r squared. So that's going to be minus 5 minus 2 all squared plus minus 4 minus 5 minus 5 all squared. So we get r squared is equal to minus 7 squared plus 1 squared. So I get 49 plus 1, so r squared is equal to 50. So therefore, the equation of the circle required to the center is at minus 5 minus 4. Therefore, the equation of the circle is x plus 5 all squared plus y, check the center, plus 4 all squared equals 50. And we're sorted.